Well, hello and welcome back to the VaNTAGe seminar. And today we're very happy to have our final series of two talks about modular curves and points on modular curves and isogenies. And we're going to start with the talk of Barinder Banwait, who's speaking about explicit isogenies of prime degree over number fields. And oh, is it all right for us to video this talk?
Yes, that's fine.
Okay, thank you.
Okay, well, I'd like to start by thanking the organizers, Drew and Rachel, for the invitation to speak in the seminar. I'd also like to thank everyone for tuning in to listen to what I have to say. There are so many things that you could be doing right now, and I'm very grateful for your presence, so thank you. Okay, so I'm going to be talking about isogenies of prime degree for elliptic curves. So I'm going to start with a quick run through of the basic definitions. So I'm going to take two elliptic curves, E1 and E2, over a number field K. GK is going to be the absolute Galois group. So recall that an isogeny between E1 and E2 is a non-constant morphism, which maps the base point to the base point. So this is usually the first definition, and then one shows that these are precisely the non-constant morphisms that induce a group homomorphism between the underlying groups of geometric points. Equivalently, it's those non-constant morphisms that have finite kernel, and this is what you might use in higher dimensional abelian varieties. So every isogeny has a degree, which in this case is just the size of the kernel. And you say that the isogeny is K-rational if it commutes with the Galois action in the following sense. So if you take sigma any Galois conjugation and you consider this square, where the horizontal arrows are the isogeny and the vertical arrows are the Galois conjugation, then this square should commute for every sigma. Equivalently, the kernel should be Galois stable. And you say that the isogeny is cyclic if the kernel is a cyclic group. Okay, so those are the basic definitions, but what are we actually trying to do in this talk? So on some vague philosophical level, we're trying to understand rational isogenies. Now, it turns out that any isogeny can be composed as a cyclic isogeny together with multiplication by m for some m. And again, in some kind of vague sense, we understand multiplication by m. So this goal boils down to understanding cyclic rational isogenies. I've been intentionally vague and imprecise in this slide to try to convey the motivation for what I'm doing here. Here's a more precise question that you could ask. So if you fix a number field K and you vary over all elliptic curves over K, and you look at all possible cyclic isogeny degrees you get, then what is that set? What is that set of integers? And stated this way, this is an open problem, but I'll come back to say something about this in the final to-do section. For now, though, as I said, we have a set of integers, so we'll give it a name. We'll call it Isog PrimeDeg K. And when you have a set of integers, you can consider the primes in that set. So we'll call the subset of primes Isog PrimeDeg K, and entries in this will be called isogeny primes for K. So P is an isogeny prime for K if there exists an elliptic curve over K that admits a K-rational P isogeny. Now, a priori, these could be infinite sets. So to clarify what this question is asking, if it's a finite set, then write it down, exactly determine it. But if it's infinite, then somehow classify this infinite set. A basic question here is what's going on for K equals Q, like the simplest number field. So in 1978, Mazur proved not only that Isog PrimeDeg Q is finite, but it is exactly this set of 12 prime numbers. Moreover, in the introduction to Mazur's paper, he considers the more general problem of cyclic isogeny degrees, and he reduces its determination to 5 composite values that he's not able to determine. And thereby, in a series of 4 papers, Kenku deals with those 5 values, from which we have a complete answer to that dream made precise for K equals Q, namely that the cyclic isogeny degrees for elliptic curves over the rationals are exactly the integers from 1 to 19 and these 7 other values. And I want to highlight one ingredient of Mazur's proof. So it's actually step 1 in his 4-step approach. So if you consider the modular curve x naught n, and you map it into its Jacobian via the Arbor Jacobi embedding, and then you project down to a certain quotient called the Eisenstein quotient, J tilde, then this map is a formal immersion along the infinite cusp in characteristics 3 or higher. So this is a very key result. It's so key, I'm even going to virtually highlight it with my virtual Zoom highlighter. This is very important, and it'll be coming up a few times in this talk. I'm not going to spend too much time on what a formal immersion is. To be fair, the definition doesn't take too long to state. So it's that the induced map on the completion of local rings should be surjective. But if this is the first time you're seeing it, then as a first approximation, you can get away with thinking that basically this is saying that F is injective. Okay, so now I'm going to fast forward a bit to the 90s, or I should do something like that. Okay, fast forward to the 90s when Momose writes this paper, Isogenies of prime degree over number fields. In this paper, Momose gives a classification of isogenies into 1 of 3 types, according to the so-called isogeny character, which is what you get when you consider the Galois action on the kernel of an isogeny. So that gives you like a 1-dimensional Galois representation. So what does Momose prove exactly? So if you have a number field K, he proves there is a constant C0 depending only on K, such that whenever you have a prime P larger than that constant, if you have an elliptic curve with a K rational P isogeny, then the isogeny character must fall into one of the following three types. Okay, so that was a bit of a mouthful. It basically is saying eventually you get three kinds of isogenies. Okay, so what are these three types? So type 1 is that the 12th power of lambda is either trivial or the 12th power of the mod P cyclotomic character up to an unramified character. Or type 2 is that the 12th power of lambda is the 6th power of the mod P cyclotomic character, but this can only happen if P is 3 mod 4. Or type 3, so in this case, K must contain a Hilbert class field of an imaginary quadratic field, and P must split in that imaginary quadratic field. So this is looking immediately like these are coming from CM isogenies. And then there is an explicit expression for how Frobenius elements act under lambda to the 12th. Anyway, so these are the three kinds of isogenies. And Momose goes on to say a few things in each of these three cases. So what does he say about type 1 isogenies? So he proves that if you have a number field of degree at most 12, then there are only finitely many type 1 primes for K, a type 1 prime being a prime for which there is an elliptic curve with a K rational P isogeny of type 1. And I want to say something about where this degree at most 12 restriction comes in. So the way Momose proves this theorem is to use a generalization of the idea I highlighted in the previous section, so this formal immersion criterion, but generalized to the d symmetric power modular curve. So this is where you take d copies of the modular curve in product and you mod out by the action of the symmetric group. So points on this high dimensional variety correspond to effective degree d divisors on the curve itself. And we need an analog of that map F we had earlier. So that's going to be this FP upper D. So this is where you take a divisor and you map it to the linear equivalence class of D minus D times infinity. And then again, you project that down to the Eisenstein quotient. Strictly speaking, you're reading modulo a certain abelian subvariety, which I'm not going to get into the details of that here. But what is this formal immersion criterion? It's this one. And this is where the degree at most 12 restriction comes in. So for degree at most 12, there are constants AD and BD, such that for primes P and Q larger than these respective bounds, you have a formal immersion at infinity and characteristic Q. So the history of this result is that this was proved for degrees at most 8 by Kamieny. This was unpublished. The details then appear in this paper of Kamieny and Mazur, and then Abramovich extends it from D at most 8 to D at most 12. These constants AD and BD were not made explicit, apart from D equals 2, which I'll come back to in this quadratic isogeny prime section. And the way they proved this was to use Kamieny's reformulation of this formal immersion criterion in terms of linear independence of Hecker operators associated to the Eisenstein quotient in positive characteristic. So you can read about that in Kamieny's 1992 IMRM paper. And why were they interested in statements like this? So in the same paper, Kamieny proves that if you have this formal immersion criterion, then you get a very important corollary. You get the strong uniform boundedness conjecture for torsion on elliptic curves. So this came up in Pete's talk last week. If you haven't seen it before, I'll be stating it in the next section anyway. For now, I just want to frame one piece of intuition that I've been trying to show here, which is that if you have these explicit formal immersion criteria, that allows you a control on these type 1 primes. Okay, so that was type 1. What about type 2? So Momose gives a necessary condition that type 2 primes have to satisfy, and it's the following. If you take a rational prime Q that admits a prime ideal of K above it, which has odd residue characteristic F, odd residue degree F, such that Q to the F is less than P over 4, and some other condition, let's forget about that, then Q does not split in Q or join root minus P. So this is not how you'll find it in Momose's paper. This has been augmented with work in progress with Martin Derricks that I'll be saying more about in this isogeny prime section. This kind of necessary condition actually goes back to Mazur's original proof. So towards the end, he proves this claim that if the above case occurs, above case here means that n is a type 2 prime effectively, then for all odd primes p less than n over 4, we have some Legendre symbol condition. And this wraps out to saying that p does not split in Q adjoint root minus n. And Mazur is able to go from this claim to proving that Q adjoint root minus n is class number 1. And therefore, he can apply Baker-Starker-Igner to say that n must be one of these 5 values. And the proof to go from this claim to this having class number 1 uses nothing more than undergraduate algebraic number theory. He's even computing Minkowski constants here. But doing this explicitly for general K is much harder. Nevertheless, Momose is able to determine the following ineffective results: that for a quadratic field, there are only finitely many type 2 primes. And if you're willing to assume GRH is true for any number field, this is attributed to Kumar-Murthy. Okay, and for type 3, right, so as I said, these look like they're coming from CM isogenies. Momose thinks so too. He he tries, but he believes really expected to be almost all of these type 3 isogenies he believes come from CM, arise from CM. But he's not able to prove this in full, and he gets some partial results, which you can find in the final section of his paper. As far as I'm aware, this is still open, so I'm going to call this Momose's conjecture, which is that for a number field K, almost all of the type 3 isogenies arise from CM. Now, after Laurie Watson's talk in the VaNTAGe seminar 3 weeks ago, I was wondering, has this conjecture been proven now, perhaps in different language? So in particular, does it follow from recent developments in the realm of isolated or sporadic points on modular curves? I'm afraid I don't know enough about this area to just say straight up to give an answer, but perhaps people in the audience do. So I'm throwing this out there. This also came up in Pete's talk last week. So he mentioned these sporadic CM points. And one place to start with this could be to watch their respective VaNTAGe talks. For now, though, I'm just going to summarize Momose's work. So he proved, so if you assume GRH, if you have a number field that does not contain the Hilbert class field of an imaginary quadratic field, and yeah, of course, yeah, the degree is at most 12, then this set of isogeny primes is finite. And this is true unconditionally if K is a quadratic field, but these are ineffective. So a natural question is to say, well, can you make it effective? In particular, can you write down this set of isogeny primes for any other number field apart from Q? So I'll get to thinking about this question in the section after next. For now, I just want to, this came up in the last section. So the strong uniform boundedness conjecture. So this was the conjecture that for if you take an integer d, then there is a uniform bound on the size of the torsion subgroup of any elliptic curve over any number field of degree at most d. And as Pete mentioned in his talk last week, this was proved by Morel in '96. So this was effectively his PhD thesis. More specifically, Momose proves this can be any criterion for general D, so this linear independence of Hecker operators, but not associated to the Eisenstein quotient, rather a different quotient, in fact, a larger one, the winding quotient. So these winding elements and winding ideals, these go back to Mazur's '77 paper. So you can read about those in chapter 2, section 18. But Morel seems to be the first person to actually consider the corresponding quotient of J or N corresponding to that ideal of the Hecker algebra. And yeah, so it's in fact the largest rank 0 quotient of J or N. So intuitively, since it's larger, it's easier to formally immerse into it. So you end up with tighter formal immersion criteria. And Morel was able to make this explicit. This AD and BD one can write down, but indeed this was done for general D. So if we come back to the Momose summary slide from the previous section, then after Morel's work, you can get rid of the degree at most 12 restriction. Okay, so now I'm going to get to thinking about this question, about trying to make this effective. So can you write down the set of isogeny primes? And the reference for this section is this recent preprint of mine. So yeah, I was interested in trying to write this down. And so for any number field, that's not Q. So it makes sense to start with a quadratic field. So I'm going to take a quadratic field that's not imaginary quadratic of class number 1, because those 9 fields admit infinitely many isogeny primes coming from CM. And hereafter, the phrase isogeny finite will refer to such a field, quadratic but not imaginary quadratic class number 1. So the first thing I tried here was to apply the following two-step approach. First, try to find an upper bound on this set of isogeny primes. And then come up with a method for each prime up to that upper bound, check whether or not that prime is an isogeny prime. So this is the same approach used by Bilu-Parent-Rebolledo when they determine exactly what the split Cartan primes are. So it was reasonable to try it here as well. So what can we say about an upper bound for the isogeny primes? So there are 3 kinds of primes here. So you have the type 1 primes, the type 2 primes. You don't have type 3 primes here because you're not imaginary quadratic of class number 1. And then you have the Momose constant C0. So recall, you only have these 3 kinds of isogenies eventually. So C0 is the constant only after which you have 3 kinds of isogenies. So you need some control on this constant as well. So there had been efforts by various people to try and make this explicit. So the Momose constant, this was worked on by Agnès David in her paper. So she came up with a fairly explicit expression, but for this constant A, which is an effectively computable absolute constant that was not given. The type 1 primes, so another thing about these is that they become torsion primes in a degree 12 extension. So you can apply the Österle bound by replacing D with 12D. And the type 2 primes, so in particular, this was looked at by Larsen and Weintraub, that they do rather more things in their paper, but in particular, they get this result, that the product of these type 2 primes is bounded by an explicit expression, but for this constant C2, which is again one of these effectively computable absolute constants. This almost gives an explicit upper bound for the isogeny primes for a quadratic field. But it was ineffective for the same reason. And you might guess that this is coming from an application of the effective Chebyshov density theorem, which is indeed the case. There do, however, exist completely explicit versions of effective Chebyshov density. So, for example, there's theorem 5.1 of Bach and Sorensen, which is free of unknown constants. So augmenting the work of David, Larsen, Momose, and Weintraub with explicit effective Chebyshov density, one is able to get an algorithm for computing an upper bound for these isogeny finite quadratic fields, which moreover one can code up in a few lines of Sage. So I ran this for some small number fields, and I was dismayed to get these kind of numbers coming up, because I mean, this put the whole method into disrepute, really. Like, there's no way you're ever going to be able to check all primes up to 10 to the 308. I mean, that's just not going to happen. So I thought, okay, we need to improve this bound. So I returned to Momose's paper after 10 years. And at this point, I'm afraid the audience is going to have to indulge me in a spot of reminiscing for a slide or two. So this problem came to me via my PhD advisor, John Cremona. So I go into his office one day and he's like, right, Barinder, it's been 6 months, time for a project. Mazur did this for Q in 78. Can you do it for any other number field? And I was like, huh, interesting. So that's when I started reading Mazur's 78 paper and studying about these optimal quotients and formal immersions. And John helped me through those first steps, for which I am very grateful. And then soon thereafter, Jim Stankiewicz brought Momose's paper to my attention. And so I started studying about these types and the isogeny character, but I wasn't really able to make progress on this back then. So now fast forwarding 10 years from that point, so this is last year now, I attended this Simons collaboration workshop organized by Jennifer Balakrishnan, Noam Elkies, Brendan Hassett, Bjorn Poonen, Drew Sutherland, and John Voigt. And I'm very grateful to the organizers of that workshop for allowing me to participate, because on the first day, I had this Zoom conversation with Isabel Vogt, in which she very clearly explains to me this idea of Lewis Dieulafoy. So Dieulafoy, so this is in a different context. So, but it's similar. So Dieulafoy is also trying to compute exactly a set of primes that he's interested in. So this is the non-surjective primes associated to a generic genus 2 curve over Q. I'm not going to get into the details of that here, but I will try to, in very broad brushstrokes, explain this idea, or at least this part of his approach. So he takes, so one takes a finite number of what are called auxiliary primes. So these are Qs. And for each one, you can compute a handful of integers. And then you take the LCM of that, right? So for one Q, you now have one integer. And it turns out that the primes that you're after, these must divide this one integer. So the prime support of this integer gives you a superset for the set of primes you're interested in. Okay, and then you do it for another auxiliary prime and another one. You do it for 10 auxiliary primes. And then you take the GCD of the resulting integers. That is still a superset for the set you're interested in. And the reason for taking 10 rather than just 2 is because you have more divisibility conditions. So you have this sieving going on, and you can end up with a fairly tight superset of what you're interested in. So when I returned to Momose's paper, so this is back in November of last year, after having worked on that problem, I was thinking about it in the following way. Forget an upper bound. Can you instead find can this method not work? Can you not find a tight superset using this auxiliary prime idea? So I ran with that idea for a while, and eventually I identified these integers. I'm afraid I don't have too much time to get into this right now. So you can either read the paper for more details, or I am going to be speaking about this in a few weeks' time in Bayreuth. So I've checked with the organizer there, Timo Keller, and it's open for anyone to attend. So do consider doing that if you want to see me speak about this live. For now, though, so coding that up, what one gets this algorithmic result. So coding up mostly in Sage. There is then an algorithm to compute not the set in itself, but a superset for this set of isogeny primes as the union of 3 explicitly computable sets. So you have the type 1 primes, the type 2 primes, and the Momose constant C0 that got renamed pre-type 1 2 primes. That's because outside of that set, you have 2 types of primes here. So this is an algorithmic result. This is mostly coded up in Sage. You can find the command line tool. So it's a command line tool released under the GPL v3+ license. So you can find it on my GitHub at this address. There is a PariGP component to it as well, which I'll get to in a slide or two. Right. So before giving a demo of it, I want to show I want to say a few things about the implementation. So recall this piece of intuition I highlighted in the Momose section. So I also said there that there were explicit formal immersion criteria given for D = 2. So this you'll find in Camieni's 1992 Invenciones paper, in which he shows that if you have a prime larger than 61 but not 71, then you have a formal immersion in characteristics 7 or higher. So that's why in the implementation of these type 1 primes, the primes up to 71 are necessarily in the output, because below that you don't know that you have a formal immersion criterion. And this part here, this is coming from that sieving I was talking about. So the more auxiliary primes you take, the more intersections you're taking here, and the smaller this type 1 prime set will be in the end. So this auxiliary prime idea is also used in the pre-type 1 2' part, which I don't have time to get into. The type 2 primes, that it does not use this auxiliary prime idea. So what the idea here is to say, well, we have an upper bound in print. We have an upper bound, which is explicit. We also have a necessary condition that primes must satisfy. So we're just going to check all primes up to the bound, whether or not the necessary condition CC is satisfied. And checking that is satisfied is a matter of a few lines of Sage. But so the bound turns out to be pretty large. It's not as large as the DLMV bound. So for Q adjoint root 5, it's about 57 billion. Sage, at least when I tried it, wasn't able to quite handle that. So I found it necessary to do this in a rather more optimized way using parallel threading with PariGP. Okay, so we're going to run this now on this quadratic VLQ adjoint root 5. So if you were to go to my GitHub and git clone it, you'll basically get this. The main script is this quadratic isogeny primes. It takes one positional argument, which is the D that defines the quadratic field. So that's going to be 5 here. And there are various optional parameters. So the number of auxiliary primes the user can specify. So I've just chosen 2 here. The default is 5. If you run 5 and you don't have like Zoom or VS Code or things like this running, it should only take about less than 10 seconds. I've reduced it to 2 because I'm running out of time, believe it or not. So yeah, okay, so that's finished. So yeah, we get the primes up to 79 and a small number of slightly larger primes. I'm going to leave it as an exercise to say that if you increase that to 6 and you wait, again, if you don't have heavy stuff running, it should only take about maybe 15 seconds, then you will get most of these larger primes will get filtered out. So you'll only be left with the primes up to 79 and 163. It does give you a warning here. So the Sage part only computes the type, it only checks type 2 primes up to 1,000. So to check all of them, that's where the PariGP part comes in. So I'm afraid I don't have a command line interface to this just yet. So at the moment, I'm afraid one is just going to have to go in and change the value of D manually. So I've set that up to be D = 5. Okay, so one is going to run a parallel for loop on this function check type 2 from 0 to the bound. So in this case, this is about 57 billion. But because of the way the parallel threading has been set up, it does the work in blocks of 100,000. That's to reduce the communication between the primary and the secondary threads, because that adds a certain amount of overhead. So this is what one would run to check all primes up to the bound. This would take about an hour of wall time, which clearly we don't have time for. So this would be 1 billion. This would be 100 million. Let's do it for 10 million. Okay, so when I press enter, this is going to check all primes up to 10 million, whether or not the prime satisfies condition CC. And if it does, it's going to print it out to the screen. Okay, so let's start that. There you go, it's done. So it took 1.5 seconds of real time, but about 8 seconds of CPU time. So it looks like it was using 6 of these 8 threads. And we only got primes that we already knew were in the superset. So yeah, it'll take about an hour to check this for all primes up to 57 billion. But for now, if you believe me about the aux prime count 6 that I mentioned, we get this as a superset, the primes up to 79 and 163. Okay, so this is a superset, but now which of these are actually isogeny primes? So you want to go from the superset to the set itself. So how does one do this? So there are three ingredients that go into this. So one is what I'm going to call quadratic points on low-genus modular curves. So this is some work that was started by Peter Brown and Philip Nyman. So they considered the quadratic points on hyperelliptic modular curves, apart from n equals 37. And then more recently, Ekin Özman and Samer Siksek, they dealt with the non-hyperelliptic modular curves in genera 3, 4, and 5, with the restriction that the rank of the Jacobian is 0. So Ekin spoke about this in her VaNTAGE talk 3 weeks ago, and you can watch that at this YouTube link. And then most recently, Yosha Box, who was Samer's student at Warwick, he's finished now, he dealt with these genus 3, 4, 5 cases, also in the case where the Jacobian has positive rank. So this is a major ingredient that is required to go from the superset to the set itself. Another one is Ekin's earlier thesis work, where she studies the everywhere local solubility of twisted modular curves. Because the work by Özman, Siksek, and Box that stops at genus 5. That means that the largest prime considered in this work is 73. But we need to say something about 79 as well. So that's a genus 6 case. So something else was required there. And so there was a different method that is that appears in the appendix of the paper, written jointly with Martin Derricks. There is a method there, given that works in general, but it requires a certain non-growth condition on the Mordell-Weil group of the minus part of the Jacobian. So the minus part of the Jacobian, when you're going from Q to the quadratic field you're interested in, this should not change. So the rank should stay the same and the torsion should stay the same. It's not clear like how often this will be true in general. We actually managed to show that the torsion does not grow in any quadratic extension. So questions like this, more generally, like what the quadratic torsion looks like on these Jacobians of modular curves, I think this would be worthy to study in and of itself. I mean, for the method of the appendix, we care more specifically about the minus part. So that could be a part of this work. But yeah, so in general, what can one say about the quadratic torsion on these modular curves? This is related to this generalized Oggs conjecture, for which there has been some recent progress, and you can see Hua Zhongyu's recent preprint for that. Anyway, so to summarize all of that, assuming GRH, one gets the first instances of the determination of these isogeny primes for number fields other than Q, and here are some examples. So you might be asking, well, why not get it for loads of other examples? One blocker for sure is the work on quadratic points on low genus modular curves. If that could be extended to higher genera, that would be very useful in and of itself, but also it would help to get a clearer idea of what's going on with these sets of isogeny primes. Okay, so now in this section, I want to say a few things about what I've been working on more recently. So this is joint work with Martin Derricks. We have generalized the algorithm of the previous section to general number fields. So so if you take any number field that does not contain the Hilbert class field of an imaginary quadratic field, then again, we can furnish a fairly tight superset of that. Again, you don't have type 3 primes here because of the restriction on the Hilbert class field here. So you only get these three kinds again. And the key new ingredient here is this is the latest and greatest state-of-the-art explicit and tight formal immersion criteria due to Derricks, Kameny, Stein, and Stahl. So you can read about that in their paper that appeared 4 years ago, but it was recently updated. So yeah, I'm going to give a quick demo of what this is going to look like. So CD isogeny dash primes. Okay, so this is currently on a private GitHub repo. It'll be released at the same time as the paper, I imagine. So the user interface is fairly similar. It's not a D you enter anymore. It's going to be the defining polynomial, which in this case, so for this cubic Galois field is x cubed minus x squared minus 2 times x plus 1. And again, so Orcs prime count is now norm bound, a bound on the norm of the prime ideal, the auxiliary prime ideals. The default is 50. Again, I'm running out of time, so I'm reducing that down to 10. So while, so 50 should only take, again, if you don't have heavy stuff running, that should only take about 20 seconds. And yeah, let's not go into what emergency Orcs primes here are. While it's finishing, there is a peri-GP part to this as well. which is very similar to before, so I'm not going to show that. Okay, yeah, so it finished. So you get this as the superset of primes, but if one were to run that for norm bound 100, one will be able to get rid of many of those primes, and indeed one gets this as the tight superset. The primes up to 43, and these 4 are the primes. So now we're going to play the same game again. How do you go from the superset to the set itself? So here, a key ingredient is this very recent work of Box, Gajewicz, and Goodman, in which they determine the cubic points on some low-genus modular curves. Like all of them, they have tables of them. So this allows Martin and I to say that all of these possibly new isogeny primes don't actually arise. And so the set of isogeny primes for this cubic Galois field is exactly Mazur's list. And this is the first example of a cubic field in which these isogeny primes have been determined. Again, similar questions to before. Why not these more examples? Again, if one can extend the work on cubic points on these low genus modular curves, that would be very useful. And what about higher degree points? So, I mean, Box, Gajewicz, and Goodman, they do consider the quartic points. I think they get all of the isolated quartic points on X0 65. But so getting more examples here, that would be very useful. Another aspect of this work with Derek's is that we're able to get a uniform bound on the type 2 primes associated to an odd degree number field. And we spend some time optimizing this for the cubic case, and we get this bound, 253,507. This is tight in the sense that there is a cubic field that satisfies condition CC with this prime. But because condition CC is only a necessary condition, it does not mean that there is an elliptic curve which admits a cyclic 253,507 isogeny. So that's that I suppose is an open problem. But this is pointing to a deeper problem, which I'm going to call. So is there a strong uniform boundedness for isogenies on elliptic curves? So, like, for example, if you fix a degree 3, say, and you look at all cubic fields, then is there like one set of isogeny primes to rule them all? Like, are they all contained in one, or is it that they get arbitrarily large? I don't know what the answer to that is. And obviously for any other integer d, you'll have to say something about eliminating CM isogenies. So like in degree 2, I suppose you could ignore the 9 imaginary quadratic fields of class number 1. Anyway, so anything in this direction would be very interesting. I don't know what the answer would be. Yes or no, I don't have a feeling for that. Okay, yeah, so some remarks on the optimizations. I should back up a bit here. So I want to say where this number came from. So we found a uniform upper bound in the cubic case by pure thought that turned out to be about 10 to the 13. And then we ran a uniform version of this PariGP code all the way up to 10 to the 13. So that took about 15 hours of wall time. So 15 times 8 hours of CPU time. I went a few months ago. I went to a virtual atelier PariGP, and so Bill Alembert, who is one of the main developers at PariGP and a former senior colleague of mine from Bordeaux, he was showing me some things in GP2C that blew my mind. Frankly, he was able to do things hundreds of times faster than I ever thought possible. So a general question here is: can one make the implementation wicked fast? So this is a technical term for in Boston, I understand, to super duper optimize one's code. I'm thinking a little bit about this using GP2C. At that point, I don't know how far that is from doing it directly in low-level C. At least the PariGP part, really, that's using nothing more than Kronecker symbol. And there have to be like wicked fast low-level C implementations of that. As for the rest of the code, so that's using like elliptic curve and modular symbols, and I don't know, presumably that could also be done in GP2C, and I'm thinking a bit about this. But anyway, so for people who are interested in fast optimizations, this could be something to consider. Right, so I've been trying to intersperse the talk with open problems as I've been going along, but there's a few more that I just want to shoehorn in at the end here. So when I spoke about this work in Seattle and in Groningen, both Ralph Greenberg and Jaap Top asked this kind of question in the realm of arithmetic statistics. So they're both noted. So out of your 3 examples, 2 of them, you don't get any new primes. Like, how often do you think this is going to be the case? So this is getting at a kind of, what is the distribution of these isogeny prime sets as you vary over all number fields of a given degree. And I think it would be interesting to think about this from some kind of heuristic perspective. Are there some heuristics that might govern how big these would be? So I was curious. I decided to run a small experiment. Oh yeah, I should probably say this first. Yeah, so new isogeny. So I've said new isogeny primes a few times already. That just means it's an isogeny prime for a number field that doesn't come from a smaller number field. So like for Q join root 5, 23 and 47 are the new isogeny primes. Okay, so this experiment, I took all quadratic fields with mod D at most 50. And then I just wanted to see how often do we get these new isogeny primes? What are they? And to try and compile some statistics and some graphs that might try to get some indication to this Greenberg top question. So there are 54 quadratic fields here. We were actually, so using this algorithm with Derek's, we were able to decide on 38 of these. So in particular, that means we have lots more examples of the determination of quadratic isogeny primes. So on the left here, we have the imaginary quadratics, and on the right, the real quadratics. This is already painting a picture that these new isogeny primes are pretty rare. And indeed, plotting some graphs that shows it to be the case. So at least almost 3/4 of the cases, you don't get any new isogeny primes. You get a very small number of one or two extra isogeny primes. There's a whole slice of the pie that we don't know what's going on with. So this will be distributed among 0, 1, or 2. But yeah, it does look like these are pretty rare. And as for which new isogeny primes we got, well, there's not that much data here really, but so 23, that came up 3 times, 29 and 31 twice each, and once each for 41, 47, and 73. Okay, doing this arithmetic statistics kind of question more rigorously, that would be very interesting for to consider. Right, so I'm wondering, this is more of a question I have for the community, like, do people want to see these results in the LMFDB? So like these sets of isogeny primes, or possibly even the mere supersets. So reasons for why one might want to do this were expounded upon by Jeremy Rouse in his VaNTAGe talk last week. So he spent a whole 4 slides talking about the applications of Galois representations and hence a fortiori isogeny primes. So I'm not going to say anything about that here. I will just refer to his talk at this YouTube link. But this is what it could look like. So this is something I threw together in a LMFDB sandbox. So if you know what the isogeny primes are, then you just write that, here they are. If it's just a superset, then you say, okay, well, this is a superset, and you list that. This, by the way, is the superset for this degree 5 Galois number field. So these aren't just made up numbers. I'm not proposing that they go right at the top of the homepage. I just did this to get small screenshots. Okay, right. Okay, so quadratic Bilu-Parent, right. So Momose also wrote some. So he also thought about the split Cartan modular curves. I feel there's been enough progress on quadratic points on modular curves more generally to start thinking about whether one can get a kind of uniform results for these split Cartan curves. So yeah, so that would be like a quadratic version of Bilu-Parent-Rebolledo. Yeah, that might be. I think this would. I don't have a great feeling for how easy or difficult that would be, but I think it would be interesting. Right, so this is actually the first problem that I stated in this talk. So this is not about isogenies of prime degree, but about cyclic isogeny degrees. So this is more like in what Kenku did as opposed to Mazur. So this is something that I'm working on with Oana Adeskalite, who is a current PhD student of Jennifer Balakrishnan in Boston, and Philip Nyman, who, by the way, is bringing you the next episode in this season of the VaNTAGe seminar. So do stay tuned for that. I'm going to end now by remarking that these are completely open. So these kind of results and questions are completely open in the realm of higher dimensional abelian varieties. So what would a Mazur isogeny theorem look like for abelian surfaces? I mean, you can ask also about the torsion. What would a Mazur torsion theorem look like? So these are totally wide open, and anything in this direction would be awesome, really. There's more going on here. So, like, I mean, so for higher dimensional abelian varieties, you have these polarizations, and so you might worry: do my isogenies, are they compatible with the polarizations? Does that even matter? Do I get different results if I take those that are compatible or not? Or you could restrict to principally polarized abelian surfaces, say, it feels harder because less is known, at least explicitly, about these moduli spaces for, say, abelian surfaces. It feels like less explicit results there are known. So that might be, so even developing that would be interesting, but anything in these directions would be awesome. Okay, right, so that's all I had to say. Thank you very much.
Oh, thank you, Barinder. So this is a great time for some questions. William, do you want to say your question out loud, or should someone else?
Barinder, what about the slide that you just had up, but for abelian surfaces of GL2 type? So the question is about maybe a little easier.
Yeah, I did not think about that. That would probably be the first restriction to consider, because yeah, they're the closest to elliptic curves in some sense. Could you get a Mazur isogeny theorem for GL2 type abelian varieties? Yeah, again, that would be very interesting. Do you even have a yeah, so the moduli space for GL2 type abelian varieties with level structure, what do those look like? Is that close enough to the X naught ends, or yeah, that would be my first question. But yeah, yeah, that would be my first question. Do you know, William, or?
I have no clue. Just
right,
seems like a natural question.
Yes, yeah. So that would also be a very good first starting case for this problem.
Great, let's see. Any other questions?
Hey, Barinder. I mean, just
hello, Alex.
To briefly say on the same subject, I guess you want to at least, I mean, you have to restrict somehow, because you have all these restrictions of scalars of elliptic curves from CM quadratic fields among your abelian surfaces.
I see, right, okay. So in an obvious sense, it's going to be infinite. So you're going to have to, right, you're going to have to restrict them somehow, right? Well, so is it the case that if you have a CM number field and you have an elliptic curve over that, and then you take the restriction of scalars, then that abelian variety you get is going to have, it was going to admit infinitely many isogenies.
Yeah, if your CM number field has class number 1, your elliptic curve is defined over that, you'll have all the CM as endomorphisms on your abelian surface.
Right. Yeah, okay. Does that set of does that class of abelian varieties intersect with the modular abelian variety? Well, yeah, so the abelian varieties of GL2 type. So yeah, these ones that you can restrict scalars from, can they look like A sub F for F some modular new form? That's just the question. I'm just thinking out loud here, but
I think so.
Right. Okay.
Yeah, so maybe the thing to do would be to restrict to geometrically simple abelian surfaces to begin with. Like otherwise, you have to have tighter or somehow more refined restrict. I mean, what you were doing throughout the talk, restricting, excluding the things that contain the Hilbert class field of an imaginary quadratic field. Here, you get that immediately at the outset.
Yeah. Okay, so yeah, so for someone starting with this question, that's probably one of the first things that they'd have to consider. To like, what are the sort of natural families that have to be excluded from the outset?
Yeah, let's see. Any other questions here? Pete, do you want to say anything about your comment?
Not really. I think it kind of says it all. I mean, since you, I mean, it's a, so these Shimura curves are, they're parameterizing abelian surfaces that have quaternionic multiplication. So these are sometimes called fake elliptic curves or false elliptic curves, because in some sense they behave much more like elliptic curves than any other abelian surface. And so for this, I guess, to say one thing, I was kind of roughly following Mazur's rational isogenies of prime degree, But what I was doing was much easier because the hardest part of Mazur's work is to prove that a sufficiently large prime degree isogeny forces potentially good reduction away from an explicit finite set. And Shimura curves have such large endomorphism ring that, like CM elliptic curves, they have everywhere potentially good reduction. So that would basically, it's kind of a way of taking advantage of some of the features of complex multiplication without literally having complex multiplication.
Okay. That raises a question in my mind that I have for you, Pete. So these Shimura curves, like, do they admit some kind of form and immersion theory, analogous to X naught n and what Mazur does in his 78 paper?
I mean, the Jacobian of a Shimura curve is a new part of the corresponding modular curve. So they're closely related. I don't know. We could talk about this later. So I don't literally. Also, Shimura curves have no real points, so you have to take that into account. So you look at points over, non-real number fields. But off the top of my head, I'm not thinking of any. I'm not able to think of any work that addresses what you just said. But it seems like in principle that maybe that could be done. Yeah.
Mm-hmm.
Oh, great. And now, Martin, do you have a question?
Well, yeah, it's not necessarily a question, but more a remark that somewhere halfway during the talk you said that regarding the uniform version of the isogeny problem, like you give a degree and then you ask, are there infinitely many points that yeah, so yes, this one.
Yeah.
So so my suspicion is actually, well, my suspicion is the answer is that such a uniform thing exists, and some work that Michael Stoll and me have been doing also really seem to be implicating that at least over odd degree number fields, this most definitely is true, because then we can, for a lot of odd degree number fields, we can show that, or no, for a lot of modular curves of the form x naught of p, we can show that they have no odd degree points.
Mm-hmm. Right, in some kind of uniform sense.
Yes, that
right.
But it really turns out that for everything I tried in this direction in the uniform way, it turns out that all degrees are much easier.
So would you expect it to be also true for even degree fields, but somehow that's just harder to prove?
Yeah, that is what my guess is, but
right.
But I'm slightly less confident there.
Yeah, does anyone else want to chime in on that one? Okay, let's thank Barinder again.